I'm going to present our work entitled Deep Model-Based Super Resolution with Non-Uniform Blur. This is joint work with Matias Tassano and Almansa, and this work is supported by GoPro and Map5 Laboratory from Université Paris-Cité. Let's start with some context. The action cameras and mobile phone industry is trying to miniaturize the image sensors in order to have smaller and lighter devices. Such miniaturization negatively influences the quality of the images and introduces blur and noise since the photosites of the sensors are smaller. Also, such devices cannot integrate optical zoom for size reasons. Our main goal is to do single image per resolution on such images. Usually, uniform blur is considered for the super resolution problem. But this assumption is not fulfilled for many applications, such as motion blur and defocus. And as you may imagine, motion blur is the main source of blur in an action camera. In our work, we propose a plug-and-play algorithm for super resolution in the presence of spatially varying blur based on linearized ADMM optimization scheme. Linearized ADMM is the most suited and efficient optimization scheme for the problem of non-uniform blur. We also developed a deep unfolding network based on our plug-and-play algorithm. Let us first start with our problem formulation. We suppose that our low-resolution image Y is a blurry, downsampled and noisy version of an high-resolution image X. Here, the blur operator H is not in convolution since the blur is spatially varying. We suppose that our noise epsilon is Gaussian. Such inverse problems are usually solved using maximum a posteriori estimation or solved in an end-to-end manner using a deep learning network. For the maximum a posteriori, we solve an optimization problem that is the sum of a quadratic data fitting term plus a regularization. The regularization, in our case, is a deep denoiser based on Drunet architecture. In our paper, we propose to solve this optimization problem using a variant of ADMM called linearized ADMM. The advantage of our method is that it does not require the inversion of the blur operator H in comparison to the regular ADMM algorithm. Please note that the first step of our algorithm is defined as a denoising step since we use a deep denoiser for the regularization. We can use this algorithm as such to super-resolve images, but it requires that we carefully tune the hyperparameters of the optimization scheme, which is time-consuming. Also, optimization-based methods are very long to run. That's why we decided to use a deep unfolding network based on our optimization process. The idea behind deep unfolding networks is quite simple. You unfold few iterations of your optimization scheme into a neural network. Then, you use a small multi-layer perceptron to predict your optimization hyperparameters depending on the parameters of your problem. In our case, those parameters are the scale factor and noise level. Then, you train your architecture on a given dataset. The trainable parameters of the architecture are in our case the weights of the multi-layer perceptron and the weights of the deep denoiser based on Drunet architecture. Here are some results of the model on scale 2 super resolution. You can see that our model deblurs correctly all the parts in the image with no artifacts and sharper results. Our algorithm outperforms all other tested methods, even those based on transformers, and yields state-of-the-art results for super resolution with non-uniform blur. Thank you for your attention.